Hello everyone, welcome to topic 8.4, acid-base reactions and buffers. Please be aware that my children are with me and are partying hard, so if you hear screams in the background, they are still probably happy. By the end of this topic, not only should you be irritated with the yells of my children, you should also be able to explain the relationship among the concentrations of major species in a mixture of weak and strong acids and bases. Okay, so for strong acids and bases, when you add unequal amounts of strong acids and bases together, all of the limiting reagent is neutralized and the pH of the resulting solution is determined by the excess reagent as shown in this acid-base skeleton equation. To solve this type of problem, follow the steps below. You first find the moles of acid and moles of base. All of the limiting reagent will react, find the amount of excess left over from after the neutralization by subtracting the larger moles minus smaller moles, or do a pCa table with just the reactants. Divide the moles of the unreacted excess reagent by the total volume of the solution to find the molarity of the resulting solutions. Okay, you can also then use the pH square from section 8.1 to determine any of the other requested values from the question. As a reminder, when a substance completely dissociates or ionizes, we describe it as being a strong acid or base. There are 6 strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, and sulfuric for the first hydrogen, as well as perchloric acid. The strong bases are the metal hydroxides from groups 1 and 2, but not beryllium or magnesium. They are listed below. Okay, so if we are reacting a strong acid and a weak acid and a strong base, there are 3 situations that we could potentially have. They react in the equation given below. If when reacting the weak acid is in excess, it is treated as a buffer solution. A buffer solution contains relatively high concentrations of conjugate acid-base pair. If a small amount of a strong acid or a base, so limiting strong acid or strong base, is added to a buffer solution, the buffer solution resists the changes to the pH. So the Henderson-Hasselbalch equation can be used to determine the pH of the resulting solution, and that equation is given below. You can hard math it without that, and it works, but this makes the whole process much easier. So you get to skip the ice table. If a strong base is in excess, then the pH of the resulting solution will be calculated from the molarity of the solution formed from the excess moles of base divided by the total volume. This is similar to a strong acid with strong base as shown above. If we have equal molar amounts of weak acid and base, then the pH of the resulting solution is determined by the conjugate base of the weak acid, because that is the species left in the solution at the end when all the reaction is done, but it forms an equilibrium state with its conjugate acid. So you have to do some back calculations to figure out its pH. And the steps are given below. You ice table, you determine Kb because Ka is usually given, and use the moles of the conjugate base and total volume to find the initial molarity. And the ice table skeleton or base equation is given to you there, like baseline equation. For a weak base and a strong acid, it's a similar process to a weak acid strong base. If the weak base is in excess, you use the Henderson-Hasselbalch equation. If the strong acid is in excess, then the pH of the resulting solution is determined by calculating the molarity of the excess moles of the strong acid or hydronium ion. If the weak base and strong acid are equal molar, then it's at its equivalence point and the moles of acid and base are equal. And so then you can determine the pH by the conjugate acid of the weak base. So it's flipped. The conjugate acid is still present in the solution, so it'll form an equilibrium with its base, and you have to determine what is present. And then if we have a weak acid and weak base, they are combined and they will reach equilibrium, and you will determine that as it is shown there. Usually there's not a lot of weak acid, weak base expected on the AP test. And we can scroll up and see if there is Okay, it's a very, straightforward, hey, just know that they reach equilibrium when they react. Okay, so here we go with the first I do. If 100 milliliters of a 0.1 molar acetic acid solution is added to 100 milliliters of 0.1 molar potassium hydroxide, calculate the pH of the resulting solution. The Ka of acetic acid is given. So, great news, they are equimolar. So like we look at this, same concentration and volume, same concentration and volume. So these are equimolar. So it is at its equivalence point. So if we look back to our stuff, if it's at its equivalence point, the conjugate base is the only species present that'll undergo any reaction. So we need to look at its equilibrium with it's the acid. So the conjugate base of acetic acid, because that's the weak acid, is CH3COO minus, because its leading H is the one that is donated. And so when we form the conjugate base, this is our conjugate base. It is going to react with water. And because it's at equilibrium, we use an equilibrium arrow, and it is at equilibrium with its COOH, and it's aqueous, and the hydroxide ion that's reformed when the conjugate base accepts the hydrogen ion from water. Okay, so in order to do the ICE table, we need to know the concentration at the equivalence point of the conjugate acid, or conjugate base, my apologies. So in order to do that, we know that when it all reacts, the amount of moles here is going to be the amount of moles of this as well, from the balanced reaction between potassium hydroxide and acetic acid. So if I figure out the moles of the acetic acid, so that would be the 0.1000 liters, because divide by 1,000 to get liters, times 0.100 molar is 0.0100 moles. Okay, then to find the concentration, we take the CH3COO minus, and we take the amount of moles produced from the reaction, and we're going to divide it by the total volume, and in this case that is 0.2. Right, 100 and 100 is 0.200 liters. So then we do 0.01 divided by 0.2, and you should get 0.0500, and there should be a third zero there. And that's molarity, and that is the concentration of our conjugate base. Okay, since we know that, we can now do an ICE table, where this is 0.0500, because at the equivalence point, it's going to take the amount of our conjugate base and reestablish equilibrium with its acid. So now the conjugate base becomes the base, and acetic acid is now the conjugate acid for this expression. Okay, we know it's going to react in a proportion of X, that we have none of these at equilibrium because they've reacted. So I'm going to add X because we're going to make them. So 0.500 minus X, this is just X and X. Okay, so we're ready almost. This is for a base, but we were given that Ka is equal to 1.8 times 10 to the negative fifth. Well, we actually need Kb, and we know that that is equal to Kw divided by Ka, and that Kw is 1 times 10 to the negative 14. So we're going to divide that by 1.8 times 10 to the negative 5. And because this is a base, so the one we're working with above is a base, we need Kb for the equilibrium. So we calculate this, and you should get 5.6 times 10 to the negative 10. So now we're ready to write our KB expression, and using the equation above, it's going to be CH3COOH concentration times the hydroxide ion divided by the acetate ion. And we know that has to be equal to the 5.6, so we're going to plug in the values we know. 5.6 times 10 to the negative 10 is equal to x times x over 0.0500 minus x. I taught myself how to do the solver on my calculator. You know, YouTube. YouTube's great for that. And I got that x was equal to 5.3 times 10 to the negative 6 molar. And that is equal to the hydroxide ion concentration, because we said that in our ice table above. So the question asks us for pH, but we can find POH first. And that's equal to the negative log of the hydroxide ion concentration, which is 5.3 times 10 to the negative 6. So then our POH is equal to 5.28. pH we know you can get by subtracting the POH from 14, and you get 8.72 as your final answer. It's a little long, and I will say that on the AP test, they will scaffold this. This would not be a one-point question. It would be broken up into several steps. So it'd be multiple steps over the whole thing. Okay, then looking at our we do. What is the pH of a solution that is composed of 500 milliliters of a 0.250 molar sodium hydroxide and 400 milliliters of a 0.2 molar hydrochloric? Okay, we see we don't have equal amounts of either one of these. So this is a strong acid, strong base. They are not in equal amounts. But that does mean, since they are strong acid, strong base, it is a one-directional arrow, not an equilibrium arrow. So when we do sodium hydroxide plus hydrochloric acid, we know it's going to go to completion and form water and sodium chloride. However, we know that one of our reactants is going to be in excess. I want you to take a minute and use a BCA table. You're going to find the moles of each first. So for this one, you are going to first, and then we'll check back in, use the BCA table, finding the moles of each one first from their concentrations and volumes to determine the excess amount of which reactant. So please pause the video and do that now. Okay, so you should have determined that sodium hydroxide was in excess because they react in a 1-to-1 ratio, and you have a lot more sodium hydroxide than you do hydrochloric acid. And so using a BCA table, you should see that you find 0.045 moles of sodium hydroxide. From here, we will use these moles and determine the concentration of sodium hydroxide, or the hydroxide ion. They are equal, by dividing the moles that we found that were in excess by the total volume of solution. Now that's 400 milliliters plus 500 milliliters is 900 milliliters. And when we change that to liters, we end up with 0.9000 liters. And you end up with a concentration of 0.050 molar for the sodium hydroxide and hydroxide ion. So then we can find the POH for this by taking the negative log of that. And you end up with 1.30. And then the pH, which is what you were asked for, is 14 minus that. Okay. Which is 12.70. Okay, so that concludes the I do and we do section of the notes. Work on the you do using your notes in the example problems, and thank you for tuning in.